Good afternoon. I'm Victor Lee from the University of Hong Kong. This is a joint project between Hong Kong U, Cambridge University in the UK, and Hong Kong UST. And I see that some of our colleagues are here. For example, Dr. Jacqueline Lam. She's also a co-PI and also co-leader of this project. So air pollution has been a major problem, both in Hong Kong and in the rest of the world, especially in cities like Beijing, London, Los Angeles, Mexico City, New Delhi, and so on. It is expected that by the year 2060, according to the OECD, that there will be 6 to 9 million deaths due to air pollution, with a cost of about 1% of the global GDP. So it is a major problem that we need to tackle. So what is the major research challenge? The major research challenge is we don't know what the air quality is among us. Okay. For example, in Hong Kong, there are 18 air quality monitoring stations, but there's no air quality station at Pok Fu Lam. So if I ask you what is the air quality right now, the answer is I don't know. In fact, you look at this map, you will see that these are where the air quality stations are located. So in most places, we don't know what the air quality is going to be. Okay. So how do we solve this challenge? So one way to solve the challenge, the naive brute force approach is, well, 18 is not enough. Why don't I put 5,000? Just spread it all around the city. Now, the problem is these things are very expensive. They cost several million US dollars, actually tens of million US dollars to build one, plus maintenance cost is more than 1 million US dollars per year. Not to mention that in Hong Kong, you cannot afford the piece of land that these air quality stations sit on. One example is the air quality station in Central, which is in this triangular piece of land right next to the landmark shopping center. So next time go to Central, take a look at it. Okay, it's a prime piece of real estate in the middle of Central, so it's very expensive. Okay. So how do we overcome this problem? Okay. Well, our mission is AI for social good. Okay, so we want to use AI technologies to help the society. Okay, and obviously, improving the health of the citizen is an important consideration. So how do we do this? We want to have the citizen avoid bad air. Okay, how do we do that? We need to let them know where the bad air is. And we need to let them know to the street level. So you see that our resolution is up to grid of 100 meter by 100 meter. Okay. As a result, what we're trying to do is we divide Hong Kong into small grids of size 100 by 100 meter. And we want to estimate what the air quality is for each of these small grids. So how do we do this? Well, we think about what are the things that drive air pollution. And immediately you think about traffic congestion, wind direction, wind speed, urban morphology, that is where the tall buildings are, whether there's a street canyon effect, and so on. Okay? So in Pok Fu Lam, there's no air quality monitoring station, but we do have data on traffic congestion, wind direction, wind speed, and also the urban morphology. Okay. So that's how we solve that problem. We use those data as proxy data to estimate and forecast air pollution. So these are the challenges of our project. So I mentioned the first one already. We have sparse air quality monitoring station. So we want to build a deep learning model called Deep Air to estimate and forecast air pollution. Our forecast is for the next 24 hours. Unfortunately, for deep learning, you need input data. So as we say, garbage in, garbage out, right? You don't have good data, you're going to get garbage out. Unfortunately, a lot of the data is missing. Okay, so we need to fix those missing data. So we've developed some AI-driven models to fix those missing data. Then even if you have the data, you have to make it comprehensible to the ordinary citizen. And that's why we've developed Yumi Air, which is an app, which, by the way, every one of you can download for free. It's been deployed, which will allow you to estimate what is air quality around you. Then we want to study the causal relationship between health and health perception and PM 2.5, 1.0, and NO2 exposure. There are actually quite a number of studies on the relationship between PM 2.5 and health status. But we want to study, in addition to health status, also health perception, how you perceive your health is going to be. And also we want to study PM 1.0, which is the particulate matter of diameter 1 micron. Okay. Then we want to quantify the impact of smart intervention on individual behavior change. The idea is, if I give you information on what the bad air is, and if I give you alternative travel paths to try to avoid the bad air, will you actually follow my advice? Okay. Okay, so task one, okay, is to develop this deep air model. As I said, we use data which is readily available, which influence air pollution. We call those proxy data. So these things include congestion data from the transport department, which, by the way, they update the congestion data every 5 minutes on all the major road segments in Hong Kong. Then we get meteorology data from Hong Kong Observatory. That's the wind direction, wind speed, humidity, temperature, precipitation, and so on. Then we get urban morphology data from the lands department, which tells you where the tall buildings are, the density of tall buildings, how tall they are, and so on. And from that information, we can calculate where the street canyons are. Okay. And also, we get information from the Environmental Protection Department, which manage the 18 air quality monitoring stations. So what we basically are doing, we are transforming the 18 EPD air quality stations into 110,000 virtual stations, because there is 110,000 100-meter by 100-meter grids in Hong Kong. Okay, so this is probably a little bit too detailed, but the rough idea is the following. In deep learning, there are models. One of them is called a convolutional model. And convolutional model deal with the spatial correlation of information. Whereas there's another model called the LSTM model, which deals with temporal correlation of information. And in air pollution, we have both spatial and temporal correlation of information. Imagine if I tell you that the PM 2.5 right now is 20 microgram per meter cube in this location, then in the next hour, it will probably be still around 20 microgram per meter cube, unless you have a fire or something like that which generates a lot of soot. Okay. So there's temporal correlation, and obviously there is also spatial correlation, because if the air quality is very bad in this particular location, then it will probably be bad in the adjacent location due to diffusion. Okay. So our model is a hybrid model, which is an integration of both the spatial and the temporal correlation. And we call it deep air. Okay. And as a result, we are able to come up with, this is a screenshot of our app, which I'll cover a little bit more later. This will have the 24-hour forecast, and this is the air quality map. An important consideration in AI models is also interpretability. Okay, so this morning I saw some talks based on AI and medicine, and I find that one of the important factors, of course, is you want to explain to the patient why your AI model tells him he has lung cancer. You cannot just walk in there and say, okay, you have lung cancer because the AI model tells you have lung cancer. You need to explain to him why, okay? So interpretability is important, and it's also important for us because suppose I say that for a particular location, the PM2.5 is very high. Why is that, okay? Or the NO2 is very high. Why is that, okay? And this picture gives you the saliency score of different pollutants and different factors. For example, look at this here. This is PM2.5. The higher the bar, the higher the saliency or the importance. You find that for PM2.5, except for the other pollutants, which of course impact this particular pollutant, the important ones are things like the meteorological factors, like wind direction, wind speed, and so on. On the other hand, if you look at NO2, you find that the most important factor is actually the urban morphology, like the street canyon, the building's density, and so on. And this makes sense because we know that NO2 is caused by traffic. And the traffic in this street canyon area, they tend to accumulate. They cannot be blown away. Okay, so this is the task 2, which is how we recover the missing data. Okay. We find that for the air pollution data, which is reported by the government stations, about 5% of the data is missing. They're missing due to faulty equipment or due to transmission failure and so on. Okay. Now, we are also relying on other factors, like the traffic congestion data, the meteorology data, and those data, the missing percentage is about 10 to 12%. So it's actually quite a bit of missing data. So the question is, how can you recover this missing data? Okay. We have actually developed 3 different ways to do so, but today I'll just talk about one of them. So this particular one is based on something called long short-term context encoder. This method was actually developed originally in image processing. So assume you have an image, and suppose one part of the image is fuzzy. Then the question is, how can you use the rest of the image to fill in that fuzzy part? Okay. Now, if you look at what we are doing here, we also have sort of an image. Because we divide the Hong Kong city into grids, right? So for each grid, we have air quality or traffic or meteorology data. So if you look at a particular set of data, like the PM2.5 data, they look at it and see it's actually an image. Okay. Now, some of them is missing. So the question then is, how can you recover those missing parts using the rest of the data? Okay. Now, if we are just using a straightforward application of this long short-term encoder, we probably cannot publish the paper. Not enough novelty, right? So what are the novelties that we have introduced? We have introduced something called an expert-driven deep learning model. The idea is, while we are using a deep learning model, we modify it so it can accommodate expert knowledge. For example, one expert knowledge that we have included in this particular case is that air pollution, it turned out, consists of 2 components. There is the local component, which is generated locally, but there is the more ambient component, which is similar in all of Hong Kong. So there's this ambient part, and then there's a local part. Okay. The ambient, and by the way, there are different arguments, but some people think it's actually blown over from across the border, okay? Now, that part of it is due to that. But there's also a part of it that we generate locally because we still have coal-burning electricity generation in Hong Kong. Okay. But just adding that one will already improve the estimation. Okay. And then we have other expert factors that is important, like the difference between weekday and weekend, and the difference between peak hour and non-peak hour of the day. Like the rush hour, obviously, there's going to be a higher air pollution. Okay. So using all that information, we're able to get more accurate recovery of the missing data. Okay, and finally, after developing this algorithm, then we say, how can we help the citizen? So we developed this app called UME Air app. Okay, UME Air stands for air quality for you and me. Okay, that's why you call it UME Air. And this air quality map, this UME Air, we have something called, we have this one, which basically tell you the air quality information. This one tell you the routing information. You know, it's like Google Map, okay? You want to go from point A to point B, there are 3 alternative routes with different travel times. Well, we did one more step, and that is, we give you 3 alternative paths, we give you also the expected cumulative air pollution exposure. So what that means is you can sort of travel a longer distance if you decided that you don't want to absorb so much PM 2.5. Okay? So this is a trade-off. We give you that trade-off. So when I showed this to my friend, he said, well, those of us who go hiking every weekend, that's a good app. And this is something called UME Medic Advisor. We are still working on this with our medical school colleagues. And the idea is, how can we give alert to vulnerable subjects, people who have COPD or asthma subjects? Okay, because for us, okay, if we don't have asthma or other respiratory problem, then bad air is bad, right? You just want to stay indoor. But for some of these vulnerable people, it's a matter of life and death. So you want to make sure that they are properly alerted. Okay. So actually, I would like to show you a 4-minute video to demonstrate what can be done with this UME Air app.
每個人牙齒構造都唔同，你有冇刷樓？上網
Sorry for the ad because it's a YouTube. Okay. All right. Dr. Jacqueline Lam and I, we are co-leading a $50 million RGC theme-based research project on AI big data for air quality monitoring and health management. The goal of our project is to provide air pollution information to citizens so they can avoid breathing bad air for improved health and quality of life. It is a truly interdisciplinary project, and team members have expertise in engineering, environmental management, chemistry, medicine, and so on.
Air pollution has proved to cause serious health problems in Hong Kong and elsewhere. Unfortunately, since there are very few air quality monitoring stations in Hong Kong, only 18 government stations, and only 35 in Beijing, which is 16 times the size of Hong Kong, we don't know the air quality in our immediate vicinity. For example, the closest air quality monitoring station to Hong Kong U is in Central, a few kilometers away. Our project allows us to estimate and forecast the air quality at any point in Hong Kong. down to the street level, so we can try to avoid traveling to places of bad air.
But how do we do it? We have developed Deep Air, a deep learning model. Deep learning is a special artificial intelligence technique. We gather data which influence air quality, including road traffic, wind direction, wind speed, points of interest, tall building density and location, to train this deep air model. Once trained, deep air can be used to estimate and forecast the values of 5 different air pollutants, including PM2.5, PM10, NO2, O3, and SO2, in any location in Hong Kong.
We have incorporated the outputs from Deep Air into a user-friendly Yumi Air app, which makes the air quality data and the advice provided to help our citizens to avoid bad air.
Our technology actually can be readily transferred to other cities such as Beijing, London, and Los Angeles.
Our recent work and other published work shows there is a positive correlation between air pollution level and COVID-19 infection rate, which makes it even more important to avoid bad air. We can add COVID alert and advice to the app as well.
Right now, we are at the University of Hong Kong. That is why it said Long Fu Shan on the screen. And we have the Pleasant Air Quality Health Index, which is free. If you want to know more details about the different components of the air pollutant, this is the PM2.5 at the current location. It shows that the value is 19.41 microgram per meter cube, which is below the WHO standard by 22%. If you want to find a route, you can start at any location, let's say Hong Kong U. Then you can type in the destination. Let's say we want to go to Kennedy Town. Then you press the Show Route button. Then it will calculate 3 different alternative routes. As it turned out, in this particular situation, all 3 routes are shown here. They are 15 minutes, 18 minutes, and 90 minutes. You can also, by pressing the different button, to find out what is the fastest route, what is the route that gives you the minimum PM2.5 exposure, and the minimum NO2 exposure, and the minimum ozone exposure. That way, you can trade off between traveling a longer distance but breathing in less polluted air. Okay, I guess I hope you are interested enough to download this free app and give us any advice if you want to have some, if you have some comments. Oh, why am I going the wrong? Oh. Okay, another task that we're studying is to study the relationship between the pollutant and health condition. And this is only a preliminary trial study because, as you probably know, due to COVID, our project basically is suspended. The clinical part of the project has been suspended. So we have been able to get some preliminary data. And as you can see, for example, this is the PM1.0, and this is the FEV1, forced expiratory volume in 1 second, which measures the lung condition of a particular subject. So you find that as the PM1.0 increases, then this FEV1 decreases. Okay? So the same is also observed for FVC, which is another measure of the lung volume, and for PM2.5 and for PM10. Okay. So these preliminary results although the number of subjects is small, it is actually statistically significant. Okay. But we hope to have the full-fledged result as we resume the recruitment and testing with clinical subjects. And finally, we want to quantify the impact of smart interventions on individual behavior change. So the idea is, if I give you some information or advice, would you actually follow my advice? Now, when I was discussing this with Professor Yu Long Lau, who is our co-PI from medical school, he pointed out one interesting point, and that is, he said, normally in clinical study, there is a lot of what if question. So for example, the question would be, okay, if I give you information on air quality and show you that a particular air quality is bad, would you actually avoid that location? So this is what we mean by what if, right? And then you as a subject, you think about, well, will I actually follow his advice and avoid the bad air? But our work allows us to actually get the real result. Because after I provide the advice, I actually know whether he take the advice or not. Okay, so this is one thing that is, which I find very interesting. Yeah. So in terms of academic impacts, we have held 2 international symposiums on AI for social good. So the first one was held at Cambridge University. It was May 24th of 2019. At that time, we don't have COVID yet, so we actually have international participants, and it was a physical meeting. There were over 100 participants at Cambridge. The second one we held last year, but obviously we're in the middle of COVID, so we have a hybrid situation whereby we have both Zoom participants and physical participation. Then we have this app, which has been available for more than a year. And then we also work with Cyberport so as to publicize this app to the public. So these are the big dashboard. If you travel to Cyberport, you will see the big dashboard in Cyberport. And as part of the community outreach activities of the Hong Kong Institute of Science and the Hong Kong Academy of Engineering Sciences, we have organized thematic talks, and I have given such talks in a couple of high schools. Okay. And the talk is, what is AI and how can it benefit the society? And obviously, this project was highlighted in that talk. And hopefully, we can deploy this in other cities around the world. And with that, I'll stop. Thank you.
Thank you, Professor Lee. Any questions from the floor, please?
Hi. Hi, thank you for your presentation. You mentioned you using the traffic data to
Yes.
calculate the atmosphere pollution.
Yeah.
I'm wondering, what is this traffic data like? Is it like how many vehicles passing the street corner per hour, or other kind of?
Okay. So actually, we are using, in addition to the transport department, we're also looking at the Google Map. The Google Map also gives you traffic data. Okay. Basically, it is in terms of average travel speed. And there's also something called a congestion index, which is 1, 2, 3, 4, 5, 5 being the highest congestion.
And this data is real-time data?
Is the transport department data in Hong Kong is updated every 5 minutes.
Okay, thank you.
Yeah.
Any other questions?
There's
Thank you, Professor Lee. It's a very good presentation. And I think you demonstrate the apps and software you developed by your team actually have give option for the different like travel option, even from Hong Kong U to Central right now.
Yes. Yeah.
Yeah, but the point is, like you mentioned, the 5 different pollutant type, like PM2.5, PM10, are actually not real like data, not real-time data right now. So if they're going to check the apps, so I want to go probably in the next 10 minutes. But the PM2.5, even gas pollutant data is probably 2 months old data.
No. Our data is updated every hour on the hour.
The EPD network can give you PM2.5 every hour?
Yes.
Yeah.
Well, actually, basically what we have is our model is developed based on historical data, but once it is developed to estimate the new data, all you need to do is give me the features, like the air pollutant of the other stations, the traffic information, the wind direction, wind speed. Okay, so all this information, once you give it to me, we can estimate within seconds.
Yeah, but the point is,
yeah.
if it's just between Hong Kong U and the Central, there's traffic accident.
Yeah.
There's quite congestion right now in
Yeah.
that's within only 2 minutes ago.
Okay.
So
now,
your calculation
Yeah.
is based on the past condition.
it's
So what I
based on
see, how you adjust
yes.
the data on there.
Yeah, it's based on past condition. If, for example, if there is a fire, for example, that generates a lot of soot, we will not be able to estimate it. Because our estimate is only based on the data that is available and which is updated. And the constraint is actually the EPD. They actually have data every 5 minutes, but they would not release the data every 5 minutes. They release it every hour. Okay. If they release it every 5 minutes, we can update every 5 minutes. Okay.
Okay. If
Yeah.
I may follow, for my next
Yeah.
question is, it's very good, like you using AI, developer the model, and to linking with the air quality within the health impact, and provide some of whatever warning advice to sensitive population. But the point, sometime, and the chemical and the biological composition are the key driver for the health outcome. So if you have the same PM2.5 in summer, the same PM2.5 in winter, the cost toxicity, the short-term toxicity are quite different.
Yeah.
So how you actually have the model or algorithm to reflect the different chemical biological composition to cause a short-term health outcome?
Okay. Actually, the model accounts not only for the different seasons, but it can also account for the personal health status of the subject. Yeah, I did not have time to talk about the details, but basically, in the medical version, obviously, you have to input your own information, your age, BMI, sex, and things like that, okay, and health status.
It's a very simple question. If data available for the open access, or is only you or expert can get data access, if for the other people want to use data to do the study. Yeah, if for example, you mentioned about transport data,
Yeah.
every 5 minutes available. Are those data is open or?
Yeah, it's open, yeah.
Okay.
It's open, yeah.
Oh.
All the data is readily available. Yeah.
Professor Lee, what is the usage of knowing these extra details about my own air quality exposure if somehow that extra information does not contribute to my better health? I mean by this, okay, you give me one, say like, route 1, okay, go this way to, say like, Poly U from Hong Kong U, or this way, go use the kind of this tunnel or that tunnel. But then both tunnels are polluted, and then both tunnels, that kind of pollution that kind of pollution, somehow they generate the same kind of level, magnitude of adverse health. In that case, what is the usage of that extra information about my air quality now and this place?
Yeah. Okay. I would hope that if enough people are unhappy, they would persuade the government to do something about it. For example, there are now a lot of new MTR lines, and the government is thinking about realigning some of the bus routes. With our app, they can actually find out what the high air pollution areas are. And obviously, in realigning a bus route, you obviously don't want to put the bus routes where it's already very congested and very bad air, right? So, and also, for example, I was showing this to a friend of mine. He said, oh, this is very good for me because my son has asthma, and because of your forecasting capability, and I know that my son's school is in Sunshine Pole or whatever, so I know that tomorrow around 2 o'clock is when he will do the PE class. I will call his PE teacher and say, don't send my son out there, because it will be bad for him. Yeah, I mean, there are uses for it, but obviously, I think we have to think about enough use cases before this thing can really become very popular. And we are actually thinking about commercializing it, but then we have to think about a killer app. So if you guys have any suggestions, give it to me.
So thank you for so many questions, and we hope that we can discuss more after this talk. And thank you, Professor Lee, for your very interesting and exciting sharing. Thanks a lot.
Thank you.
And thanks everyone for coming.